Hey there, welcome to another edition of Kung Fu Physics. We are working our way through practice physics GRE problems. I have a mechanics problem for you today. It's number 82 off of the 92 exam. Looks like this. As usual, when I scan a problem like this, I want to look at the answers quickly. So basically I'm looking at something that has h over md squared multiplied by some constant. 1/2, 1, 2, 3, 4, right? Doesn't really help me too much, but at least I know what I'm up against. So after that quick glance of the answers, I start into the text of the problem. Well, a quick glance of the diagram perhaps, and then into the text of the problem. Number 82, a thin plate of mass big M, length big L, and width 2d is mounted vertically on a frictionless axle along the z-axis as shown above. Initially, the object is at rest. It is then tapped with a hammer to provide a torque tau, which produces an angular impulse h about the z-axis with magnitude h equals integral tau dt. What is the angular speed of the plate about the z-axis after the tap? I apologize, this print-off is not easy for you to read. Hopefully you have this printed off at home and are working through this problem and can follow along at home and just listen to my narrations. That would maybe be best. But this is not hard to solve this problem. It's another problem, one of the couple that are on the practice exams that I would say is best solved by having a small understanding of impulse. Okay? So impulse. Now impulse, you can give something an impulse in a translational manner or a rotational manner. This happens to be the latter. We happen to be talking about a rotational impulse. But what is an impulse? Just the classic way you think about it with translational, it's a force applied over time, right? And anytime you apply an impulse to an object, it's going to change its momentum in some manner. I think traditionally you would think about it changing its translational motion. This problem is sort of challenging you to think about how an impulse, an angular impulse, would change its rotational momentum. If I said motion before, I meant momentum. So that's the key thing here. Impulses change the momentum of an object, and that's how you solve this problem. So let me get my marker out here. Really, that's all there is to it as far as so an impulse equals an integral, and let's just give the translational equivalent, the thing that we're probably more used to seeing, a force over time. So an impulse is a integrated force over time, and it's equal to the change in momentum. And you know, I may be fudging a little bit there. There may be cases where that's not always the case. Maybe all the impulse does not create a change in momentum. I would have to think about that for a second. I'm not saying I'm wrong, I'm not saying I'm right. I'm just saying that I'm not feeling 100% confident in stating this, but I think I'm on the money there, and certainly this is the way to solve the problem, so there's something to be said there. We're going to be using the rotational equivalent, though, of course, that they give us. So rather than I, they're calling this H, and we are saying that we are going to integrate a torque over time in the rotational analog to this. And I don't know what I would say for momentum if I'm using P here. Why don't I use rho here, Greek letter rho, for the change in angular momentum. And the change in angular momentum is actually really easy to get. It's just the final angular momentum multiplied by the initial angular momentum. So the final angular momentum is going to be I omega and the initial angular momentum, because it's at rest, is going to be 0. Okay. So, basically that's, we're almost done solving the problem. I'm taking a long time to explain things, but this drops out. We basically get h equals I omega, and omega, which is asked for in the problem, equals h divided by I. Okay, so we want omega, we have h, all we really need to get is I of this thing. And this was a thin plate that we're using here. And they give us the dimensions of the plate. But we can use our cheat sheet here. The one cheat sheet that they give us to use for the physics GRE is this guy, right? And it has moments of inertia. And the only thing that's even close to what we're dealing with here is the rod, 1/12 mr squared. What I want you to kind of imagine is, in this plate, if you took a slice here, you can see how this slice would look like a rod. And we're going about the z-axis. So imagine this slice out of the bottom here as our rod, and the moment of inertia of that is going to be the 1/12 ml squared. And you may be saying, wait a second, because what about this? This thing is of height L. Does that make a difference? And it wouldn't, because you're just stacking a whole bunch of these, and they're all of 1/12 ml squared, and it kind of doesn't really matter as far as contributing to the moment of inertia. Now, if the mass of the entire thing was somehow dependent on L, for example, if they give you a density, a linear or some type of density that was dependent on L, then certainly the taller it was, then the heavier it would be, and then L would certainly matter in that case. But as the problem's set up, it doesn't matter. The angular momentum is completely independent of L. So it doesn't matter how tall this thing is, it doesn't change the moment of inertia. That threw me a little bit, so I'm being a little wordy on that, but maybe there's somebody else out there that sort of threw you, that L was not factored in. But that's sort of why. You look at it carefully, and you'll see that L does not affect the moment of inertia there. So what does affect the moment of inertia is this, and basically you have to plug in correctly the distance here. And in the problem, this is set up as d over 2. I think I have that right. Oh no, I don't. This is set up as d, right? And so in our problem, L equals 2d. And this is just the little cheap thing we have to deal with here. So you plug in, this is I equals 1/12 m times 2d squared, right? And you get the 2 squared there, so you get 4/12 m d squared. That's a third md squared. And you just plug I equals a third md squared up here, and the 3 comes up to the top, and so you get 3h over md squared. And that's it. That's brought you to one of our possible answers, right? Right. D is the one that I'm going to be looking at heavily. It's 3h over md squared, and that's the one that I want to go with. So there's a little bit of a wordy explanation, but I think if you were just doing the problem and not trying to explain it on a webcam video, then you would probably be able to move through that one pretty easily if you understood impulses pretty well. So I guess the message for the day is that impulses are a change of momentum, either translational momentum or rotational momentum, and that will help you solve a problem on a physics GRE, which is what you want, right? So that's all, and I'll see you next time.